Most people think of nuclear weapons as a single invention. One button, one blast, one category of ultimate force. In reality, that image hides a much larger system. What is commonly called the bomb is actually a layered family of technologies, doctrines, and delivery concepts built around different physical principles and very different strategic purposes. At the broadest level, nuclear weapons are not defined only by size or destructive power. They are organized by how they generate energy, what they are designed to hit, and the role they play inside military planning. Some rely on fission, splitting heavy atomic nuclei such as uranium-235 or plutonium-239. Others use fusion, forcing light isotopes of hydrogen together under extreme temperature and pressure. From there, the system branches again into categories like strategic, tactical, enhanced radiation, and Earth-penetrating weapons. Each exists for a different operational logic. That distinction matters because public discussion often compresses all of these devices into a single abstract threat. But states that built nuclear arsenals did not design them as one uniform tool. They developed them as a hierarchy. At one end are early atomic designs measured in kilotons. At the other are multi-stage thermonuclear systems capable of yields in the megaton range. Between those extremes sit weapons tailored for deterrence, battlefield use, hardened underground targets, or, in theory, long-term radioactive contamination. So the real story is not just about destructive power, it is about classification, mission design, and escalation control. Nuclear weapons are best understood not as one machine, but as an entire architecture of force built over decades of scientific, military, and political competition. To understand that architecture, the first step is the physics at its foundation, the original fission weapon, and the chain reaction that made the nuclear age possible. To understand every later category of nuclear weapon, the starting point is the simplest one, the fission bomb. This is the original architecture of the nuclear age, and despite later advances, it still defines the core logic of how a nuclear detonation begins. The common misconception is that these weapons work like oversized conventional explosives. They do not. Their energy comes from manipulating matter at the atomic level. A fission weapon is built around heavy, fissile material, usually uranium-235 or plutonium-239. Under the right conditions, a stray neutron strikes one of these unstable nuclei and splits it apart. That split releases heat, radiation, and more neutrons, which then strike nearby nuclei. What matters is speed. If enough fissile atoms are packed together in the right geometry, that process becomes a self-sustaining chain reaction in a fraction of a second. But reaching that point is the real engineering challenge. A nuclear weapon cannot simply store its core in a permanently supercritical state. It has to remain stable, safe, and transportable until the instant of use. That is why early designers developed two different assembly methods. One is the gun-type design, which rapidly drives one subcritical mass into another. The other is the implosion design, which uses carefully timed conventional explosives to compress a plutonium core inward until it becomes supercritical. Those two methods reveal something larger about nuclear weapons. The physics may be simple to describe, but the weaponization process is a problem of precision engineering. Timing, symmetry, material purity, and neutron behavior all determine whether the device functions as intended or fails outright. In military terms, this first generation established the baseline, compact enough to deploy, powerful enough to destroy a city, and technologically mature enough to reshape global strategy. But once fission proved possible, The next question was obvious. If one atomic chain reaction could release immense energy, could it be used to trigger something even larger? If fission created the first atomic bomb, fusion is what turned nuclear weapons into a different class of force altogether. The misconception is that thermonuclear weapons are just larger versions of earlier bombs. In practice, they represent a separate design philosophy. Instead of relying on one runaway chain reaction, they use one nuclear process to ignite another, creating a staged system engineered for far greater yields. A fusion weapon uses isotopes of hydrogen, typically deuterium and tritium, or materials that produce them during detonation. Under ordinary conditions, those nuclei repel each other. To make them fuse, the weapon has to generate extraordinary heat and pressure. That is where the fission primary comes in. A compact fission explosion acts as the trigger, producing the conditions needed to compress and ignite a secondary stage filled with fusion fuel. This staged arrangement is the defining mechanic of the thermonuclear era. In a two-stage design, the first explosion does not simply add damage, it functions as an internal engine. Radiation from the primary is directed through the weapon casing to compress the secondary assembly, often containing fusion fuel and additional fissile material. When that compression succeeds, fusion begins, releasing immense energy and often causing further fission in surrounding materials. The result is a weapon whose yield can be scaled far beyond the limits of a single-stage atomic bomb. That shift changed more than explosive power. It changed doctrine. Fission bombs made catastrophic destruction possible. Thermonuclear weapons made it industrial in scale. Cities were no longer the upper limit. Entire urban regions, hardened military complexes, and strategic infrastructure networks could now be threatened with a single warhead. This is why the development of hydrogen bombs transformed deterrence from a theory of devastating attack into one of civilization-level retaliation. But raw yield alone does not explain how nuclear arsenals are organized. Once states had weapons ranging from kilotons to megatons, they needed a framework to decide what each one was actually for. That is where the divide between strategic and tactical weapons begins. The most important divide in nuclear arsenals is not always technical. It is strategic. Public discussion often measures these weapons by blast size alone, but military planners classify them by mission. That is the difference between strategic and tactical nuclear weapons. The distinction is not absolute, and it has shifted over time, but it remains central to how nuclear states think about escalation. Strategic nuclear weapons are designed to affect the overall balance of a war or deter one from starting in the first place. They are aimed at high-value targets such as major cities, military command systems, missile fields, submarine bases, and industrial infrastructure. Their purpose is to threaten the foundations of an opponent's state power. In practical terms, these are the weapons associated with long-range bombers, intercontinental ballistic missiles, and submarine-launched ballistic missiles. Tactical nuclear weapons, sometimes called non-strategic weapons, serve a narrower battlefield or theater-level role. They are intended for use against troop concentrations, airfields, ports, armored formations, or regional command nodes. Their yields are often lower, but yield alone does not define them. A relatively small warhead can still be strategic if assigned to a critical target, while a larger weapon can be considered tactical if its purpose is limited to battlefield effect. This distinction emerged during the Cold War as nuclear states tried to solve a difficult problem. If every nuclear detonation risked general war, could there still be weapons designed for controlled, localized use? That question produced artillery shells, short-range missiles, gravity bombs, depth charges, and other systems built around the idea of limited nuclear employment. Whether such use could ever remain limited is another matter, and that uncertainty is exactly why the category remains so controversial. In other words, nuclear arsenals are not just collections of warheads. They are structured around theories of signaling, deterrence, and escalation management. And once planners began tailoring warheads to different missions, the next step was inevitable: designing specialized nuclear weapons for very specific battlefield effects. Once nuclear planners moved beyond simple categories like atomic and hydrogen bombs, weapon design became increasingly specialized. The goal was no longer just to produce the largest possible explosion. It was to shape nuclear effects for particular military environments. That shift created a range of mission-specific warheads built to solve very different operational problems on land, at sea, and in the air. One example is the enhanced radiation weapon, more commonly known as the neutron bomb. Its design emphasized intense radiation output relative to blast. In theory, that made it more suitable for use against armored formations, where crews could be incapacitated, while nearby infrastructure suffered less physical destruction than with a larger conventional nuclear detonation. The concept reflected Cold War battlefield thinking, especially in Europe, where military planners were trying to counter massed armored forces without automatically escalating to large-scale city destruction. Another category is the Earth-penetrating nuclear weapon. These systems are intended to attack hardened or buried facilities such as underground command bunkers, storage complexes, or deeply protected military sites. The idea is not simply to detonate above a target, but to transfer more of the explosion's force into the ground. In practice, this has always faced technical limits. Penetration depth is restricted, and any nuclear detonation near the surface still produces major fallout risks. Even so, the category shows how nuclear weapon design follows target sets, not just abstract deterrence theory. There were also nuclear artillery shells, atomic demolition munitions, air defense warheads, and nuclear depth bombs for anti-submarine warfare. Each reflected a period when military institutions tried to integrate nuclear effects directly into conventional operations. That is what makes specialized nuclear weapons so important analytically. They reveal a doctrine in which nuclear force was not treated only as a last resort national instrument, but at times as a toolbox for highly specific scenarios. But specialized warheads are only one half of the system. A nuclear device has no strategic value unless it can actually reach its target. That moves the story from warhead design to delivery systems, where missiles, aircraft, and submarines determine how nuclear power is projected. A nuclear weapon is only as relevant as the system that can deliver it. That is why the history of nuclear arsenals is also a history of platforms. Public imagination often focuses on the warhead itself, but military planners focus just as heavily on range, survivability, launch speed, and penetration capability. The delivery system is what turns a device into an operational instrument. The oldest method is the gravity bomb, carried by aircraft and released over a target. This approach offers flexibility. Bombers can be recalled, redirected, visibly deployed as signals, or held in reserve during a crisis. That makes them politically useful as well as militarily important. But aircraft are also vulnerable. They depend on air bases, tanker support, trained crews, and the ability to survive enemy air defenses long enough to complete the mission. Missiles change that equation. Ballistic missiles, especially intercontinental ballistic missiles, compress decision time and extend reach across continents. Once launched, they follow a largely predetermined trajectory at extremely high speed. Submarine-launched ballistic missiles add another layer by making the launch platform far harder to detect and destroy. This is one reason ballistic missile submarines became central to deterrence strategy. They provide a survivable second strike capability even if land bases and airfields are attacked first. Cruise missiles introduced yet another logic. Instead of climbing into a ballistic arc, they fly through the atmosphere, often at lower altitude, using guidance systems to navigate around defenses and strike with precision. They are generally slower than ballistic missiles, but can be harder to track depending on the scenario. This makes them useful for regional missions, flexible targeting, and certain limited nuclear roles. Taken together, these systems form the basic map of nuclear delivery. Aircraft for flexibility, land-based missiles for rapid response, submarines for survivability, and cruise missiles for adaptive penetration. But once multiple delivery methods exist, planners face a new challenge. They must decide how to organize them into a coherent deterrent structure. That is where the nuclear triad comes in. The nuclear triad is often described as a symbol of maximum strength, but its real purpose is stability through redundancy. It is not simply 3 different ways to launch nuclear weapons. It is a structure designed to ensure that no single enemy strike can eliminate a state's ability to respond. In deterrence logic, that survivable response is what matters most. The triad consists of 3 legs: land-based intercontinental ballistic missiles, submarine-launched ballistic missiles, and strategic bombers. Each compensates for the weaknesses of the others. Land-based missiles are fast and constantly available, but fixed silos can be targeted. Submarines are difficult to locate and therefore highly survivable, but they rely on secure communication and long patrol cycles. Bombers are slower, yet they are visible, recallable, and politically useful in a crisis because they can signal intent without immediately crossing the point of no return. This layered arrangement complicates an adversary's calculations. To disarm a triad-based nuclear state, an attacker would have to destroy hardened missile fields, locate ballistic missile submarines at sea, and neutralize bomber bases and aircraft, all while preventing surviving forces from retaliating. That is an extraordinarily difficult task. The result is not invulnerability, but a far more credible second strike posture. During the Cold War, this became the backbone of major nuclear deterrence doctrine. The goal was not to make nuclear war manageable. It was to make a successful first strike so uncertain and costly that rational opponents would avoid attempting it. In that sense, the triad is an organizational answer to a strategic problem: how to preserve deterrence even under surprise attack. But maintaining a triad is expensive and technically demanding. It requires command systems that can function under extreme pressure, deliver authenticated orders, and prevent unauthorized use. And that leads to the next layer of the nuclear system: command, control, and the architecture of launch authority. The existence of nuclear weapons creates a second problem beyond physics and delivery: control. A state may possess warheads, missiles, submarines, and aircraft, but without a reliable system of command and authorization, those assets become unstable rather than deterrent. This is why nuclear arsenals are governed not just by hardware, but by elaborate command and control structures designed to balance 2 opposite demands: absolute readiness and absolute restraint. At the center of that system is launch authority. In most nuclear states, the legal and political power to authorize use is concentrated at the highest level of national leadership. That authority must then move through a secure chain of command to crews in missile silos, submarines, or bomber units. The process has to be fast enough to function during a crisis, but restrictive enough to prevent accidental, unauthorized, or fraudulent launch orders. That tension defines nearly every safeguard built into nuclear operations. Technically, this depends on hardened communications, authentication protocols, and redundancy. Orders are typically verified through coded messages, sealed procedures, and multiple-person control rules. Missiles and bombs are not meant to be used by a lone operator. They are embedded in systems that require confirmation, synchronization, and procedural compliance at several stages. In some arsenals, permissive action links and other lockout mechanisms are intended to prevent arming or detonation without valid authorization. Cold War history showed why this architecture mattered. As warning systems improved and missile flight times shrank, leaders faced the risk of making decisions in minutes under conditions of uncertainty. False alarms, sensor errors, and misread signals became not theoretical problems, but recurring dangers. That forced nuclear powers to invest not only in weapons, but in institutions capable of managing fear, ambiguity, and technical failure. In other words, nuclear deterrence depends as much on decision systems as on explosive yield. But even the best command network is only as good as the information feeding it. That brings the system to its next critical layer: early warning, surveillance, and the intelligence architecture that tells leaders what is actually happening. A nuclear arsenal does not operate in isolation. It depends on a constant stream of information about launches, troop movements, radar tracks, satellite imagery, submarine activity, and command behavior. Without that information, deterrence becomes guesswork. This is why early warning and nuclear intelligence are not supporting features of the system. They are part of its core operating machinery. The most urgent task is missile warning. Because ballistic missiles can reach their targets in minutes, nuclear states built networks designed to detect launches almost immediately. These systems typically combine ground-based radar with space-based infrared satellites that can spot the heat signature of a missile boost phase. Radar then helps track trajectory, estimate destination, and distinguish a real attack from noise, error, or unrelated activity. That compressed timeline is one of the defining pressures of the nuclear age. But warning is only one layer. Nuclear intelligence also includes monitoring adversary doctrine, force posture, readiness levels, and technological change. Analysts watch where submarines patrol, how missile units disperse, when bomber fleets are generated, and whether command networks appear active or degraded. A missile in a silo is one fact. A state shifting multiple delivery systems into alert status is a very different signal. The interpretation of those signals can shape national decisions before any weapon is launched. This produced a major institutional shift during the Cold War. Nuclear powers built integrated systems linking satellites, radar stations, listening posts, reconnaissance aircraft, and intelligence agencies into a single decision framework. The aim was not merely to collect data, but to reduce uncertainty fast enough for leadership to act. That remains difficult. False positives, incomplete information, and ambiguous military movements can still distort perception in moments of crisis. So the nuclear system is not just built on weapons and orders. It is built on interpretation under time pressure. And once states can see an attack coming, the next question becomes even more consequential. What exactly are they prepared to do in response? That is where nuclear doctrine takes over, translating raw capability into strategic policy. Nuclear weapons matter not only because they exist, but because states build formal ideas around when, why, and whether they would ever be used. That is the role of nuclear doctrine. It translates weapons, delivery systems, and warning networks into policy. The common misconception is that doctrine is a fixed rulebook. In reality, it is a strategic framework shaped by geography, force structure, alliance commitments, and how leaders interpret risk. At the broadest level, doctrine answers a few central questions. Is the arsenal meant only to deter nuclear attack, or also major conventional war? Will the state pledge never to use nuclear weapons first, or keep that option open? Does it rely on massive retaliation, flexible response, or some form of limited escalation to force an adversary to stop? Each answer produces a different kind of force posture and a different set of targeting priorities. During the Cold War, these choices evolved repeatedly. Early thinking often emphasized overwhelming retaliation, the idea that any nuclear use could trigger a devastating strategic response. Over time, that approach appeared too rigid for a world of regional crises, alliance obligations, and varying levels of conflict. In response, many planners shifted toward more flexible options, including graduated response plans and limited-use scenarios. The purpose was not to make nuclear war safe. It was to preserve credibility by showing that leaders had more than one possible course of action. This is why doctrine and arsenal design are inseparable. A state that speaks of assured retaliation prioritizes survivable second-strike forces. A state focused on regional deterrence may emphasize shorter-range systems, dual-capable aircraft, or lower-yield options. Even declaratory policy matters, because public statements can shape adversary expectations long before any crisis begins. In that sense, doctrine is the software of the nuclear system. It tells decision-makers how capability is supposed to function under pressure, but doctrine alone cannot stabilize competition. Once multiple states build arsenals around different assumptions, the next challenge becomes managing the relationship between them. That is where arms races, arms control, and strategic balance enter the picture. Once nuclear weapons became central to great power security, they also generated a new kind of competition. The arms race was not simply about building more bombs. It was about constantly trying to preserve advantage in a system where vulnerability could never be fully eliminated. Each improvement in one state's arsenal risked making another state feel exposed, which in turn drove another round of expansion, modernization, or doctrinal change. This competition operated on several levels at once. Quantity was the most visible. States counted warheads, launchers, submarines, and bombers because numbers affected perceptions of survivability and strike capacity. But technology mattered just as much. Accuracy improvements made missiles more effective against hardened silos. Multiple independently targetable re-entry vehicles allowed a single missile to carry several warheads against separate targets. Missile defenses, even when limited, raised questions about whether one side might eventually blunt a retaliatory strike. The result was a cycle in which defense, offense, and uncertainty fed each other. That instability is what gave rise to arms control. These agreements were never acts of disarmament in the simple sense. They were management tools. Their purpose was to place ceilings on the most destabilizing systems, create inspection mechanisms, and make force structures more predictable. Treaties on test bans, missile defenses, intermediate-range systems, and strategic arms all reflected the same underlying logic. Even hostile rivals had a mutual interest in reducing the chance of miscalculation or runaway competition. Verification became the key operational issue. No agreement mattered unless each side could monitor compliance through national technical means, inspections, data exchanges, and notification procedures. In that respect, arms control was not separate from deterrence. It became one more layer of the deterrence system itself, adding transparency where secrecy had become too dangerous. But strategic balance has never been static. As older treaties weakened, new nuclear states emerged, and advanced delivery technologies entered the picture, the framework became harder to maintain. That raises the next question: how nuclear weapons are changing in an era no longer defined by a simple Cold War rivalry. The post-Cold War nuclear landscape is often described as smaller, but that can be misleading. In some places, stockpiles declined. In other ways, the system became more complex. Instead of a relatively stable rivalry between two superpowers, the modern environment includes multiple nuclear states, regional deterrence equations, modernization programs, cyber risks, and new delivery technologies that compress warning time and complicate strategic signaling. One major shift is the spread of diversified arsenals. Nuclear competition is no longer defined only by the size of a stockpile, but by its composition. States are investing in mobile missiles, quieter submarines, upgraded bomber fleets, dual-capable systems, and more precise warheads. Some are emphasizing survivability. Others are focusing on regional coercion, missile defense penetration, or flexible response options below the threshold of all-out strategic exchange. That means nuclear planning today is less about a single balance and more about overlapping balances in Europe, Asia, and at the global level. Technology is reshaping the picture as well. Hypersonic glide vehicles, advanced cruise missiles, improved space-based sensors, and cyber operations all affect how nuclear forces are perceived and managed. A faster or less predictable delivery system can shorten decision windows. A cyber intrusion into warning or command networks can create doubt even before a crisis peaks. In this environment, uncertainty itself becomes a strategic variable. States are not only trying to deter attack, they are trying to preserve confidence in their own systems while undermining an adversary's. This is why modernization does not necessarily mean expansion in raw numbers. It often means replacing aging systems with more credible, adaptable, and survivable ones. But that process can still intensify rivalry because every upgrade is interpreted through the lens of intent. A defensive improvement for one state may look like a destabilizing advantage to another. And that brings the story to its final layer. After physics, platforms, command systems, doctrine, and modernization, the ultimate question is not what nuclear weapons are. It is what role they now play in the wider international order, and what pressures may transform that role next. Nuclear weapons are often presented as devices of absolute destruction, but in practice, their main role has been political. Their greatest influence is usually exerted before launch, not after. They shape alliances, military spending, diplomatic leverage, crisis behavior, and the limits of conventional war. That is what makes them different from nearly every other category of weapon. They are not simply tools of combat. They are instruments for structuring the behavior of states. This political function is visible in extended deterrence. A nuclear power does not only defend itself, it can also promise protection to allies, creating a security umbrella that alters regional balances without requiring every partner to build its own arsenal. That promise, however, depends on credibility. Allies must believe the guarantee is real, and adversaries must believe it would be honored under pressure. Maintaining that credibility requires deployments, exercises, consultation mechanisms, and visible integration between nuclear forces and alliance planning. Nuclear weapons also operate as shields behind which other forms of competition take place. States with atomic arsenals may engage in conventional buildups, proxy conflicts, coercive diplomacy, or territorial pressure under the assumption that the presence of nuclear risk will discourage full-scale retaliation by opponents. This does not eliminate conflict. It changes its boundaries. Nuclear deterrence can freeze some forms of war, while leaving room for others that remain intense, prolonged, and dangerous. At the same time, these weapons create permanent management problems. Every crisis between nuclear-armed states carries the possibility that signaling will be misread, that conventional losses will trigger fears of strategic vulnerability, or that leaders will interpret restraint as weakness. For that reason, nuclear politics is not just about possession. It is about communication, perception, and the ability to keep competition from crossing invisible thresholds. And that is the final paradox of the system. Weapons built for extreme destruction have become embedded in everyday statecraft, shaping the modern international order precisely because everyone hopes they never have to be used. The closing question, then, is how long that balance can hold under future pressure. In the end, the real significance of nuclear weapons is not contained in any single warhead type. It lies in the larger system they created. What began as a breakthrough in atomic physics became an enduring global structure made up of laboratories, delivery platforms, military doctrines, warning networks, command chains, treaty regimes, and political calculations. The public often sees isolated symbols: a mushroom cloud, a missile test, a submarine launch. The strategic reality is a tightly connected architecture designed to manage the possibility of catastrophic force. That architecture persists because nuclear weapons perform several roles at once. They deter direct attacks on states with secure arsenals. They anchor alliance guarantees. They influence how conventional wars are planned and limited. They also shape how leaders interpret vulnerability, prestige, and technological change. In that sense, nuclear weapons are not outside the international system. They are woven into it. They help define the boundaries of power in the modern world, even when they remain unused. But the future pressure on that system is increasing. Aging arms control frameworks have weakened. More actors are modernizing their forces. Regional rivalries now interact with global deterrence in more complicated ways than during the Cold War. At the same time, cyber operations, hypersonic delivery systems, space-based infrastructure, and faster decision cycles are making nuclear management more difficult. The danger is not only deliberate escalation, it is the possibility that speed, uncertainty, and misinterpretation will erode the buffers that past generations tried to build. That is the strategic reality of the nuclear age. These weapons are not merely relics of the 20th century, and they are not simply bigger bombs waiting in storage. They are components of an evolving system that still structures military power, alliance behavior, and great power competition. Their future challenge is the same as their original one: how states maintain deterrence without allowing the machinery of deterrence itself to produce the disaster it was built to prevent.